Okay, so this first part should be a little bit of review from last class since we already did it. So remember, how do you determine if something's continuous? You go through the continuity test. There are 3 steps. And on your test, there's points associated with showing every step. So the first thing you must do is find the value of the limit. You must find the y value. So here, I want to know what is the y value when x equals 2. So I plug it in. Oh dear, I have 4 divided by 0. So I'm just redoing this. All right, just going through. That way you guys can try out, see yourself. What? Okay, so it's 3, and then still 3 divided by 0 is undefined. So I don't actually have a y value. So what this means is it could be an infinite discontinuity. It could be removable. It just depends. Like, what is the limit? So although y is not defined, what are the y values approaching? What are the function values approaching as we get closer to our x value? So that's the second thing we're looking at. We're looking at the limit, right? So f of x approaches, does it approach the same value from both sides? Okay, so we can open up our calculator. Do we know what x plus 1 over x minus 2 looks like? No? Maybe? Yeah? You want to describe it? No? It's not continuous, but is it just look like a line or something with a hole, or is it, or as I get closer to 2, it's approaching infinities, right? Okay, so I know that the limit, as Lindsay Lohan said, the limit does not exist. Okay, when it approaches infinities like that, it will not exist. So we say the limit of my function, f of x, that is not readable, of my function, f of x, only when we're approaching an x value of 2, we say does not exist. Okay, so I'll prove it to you. Let me add a graph. I'm going to show x plus 1. So there's 2 ways to do it. So you have to do the x plus 1. That way it's not doing x plus 1 over x minus 2. You understand order of operations? You have to put parentheses around it. That way it will write it as a rational function. And then this is x minus 2. Cool. Yeah, you're right. So when x equals 2 right here. Oops. No. Okay. I think you guys can see this. At x equals 2, I'm approaching negative infinity from the left side, positive infinity if I'm approaching from the right side. So approach from the right side means I'm coming from the right, going up to infinity. Approaching from the left means I'm coming from the left, going down towards infinity. So I say the limit does not exist. Okay, so now the third part of the continuity test, right? So you see if it has a y value. Are we approaching the same number from both sides? So that's the limit. And then the third part is, are those equal? So clearly, like, neither one of these are defined. We don't have a y value. We don't actually have a limit. We're not approaching one number. So the third thing is we know that f of 2 is not equal to limit as x approaches 2 of my function. But more specifically, we know, okay, so we know they're not equal, so that means it's not continuous. So really this third step is like, hey, I give you something that actually is continuous, then you would just say, oh yeah, it equals, check, continuous. But here it's not continuous. And we can identify which type of discontinuity it is because it's going to be infinite. Okay, so now I want you guys to try, so we're going to go through the steps for the bottom one together. So, C. Let's see, the first step is, do we actually have a function value? Do we have a y value? So I'm going to plug in negative 3 and see what we get. Did you already do this one? I forget where do we start this one? No. Okay. Then I knew it was going to take too long. So this isn't a number divided by 0. It's literally 0 divided by 0, so it's a very special case. Do we know what it's called? It's also fine. I'm not expecting you to know what it is. Just like a trivia question. So if you divide by 0, it's undefined. But if you have a 0 over 0, huh?
0 to 0.
We call this indeterminate form because you actually can't determine what the heck is going on. If I had any number divide by 0, clearly that's undefined. If you had 0 divide by any number, All right, so 0 divided by any number is going to equal 0. Any number divided by 0 is just going to be undefined. But what if I have a 0 over a 0, right? That's weird. That's weird. Like, so we call it indeterminate because you cannot determine what the heck is happening at this one point we're looking at. So there's going to be, we haven't dealt with it yet, but there are ways to deal with this. But what we know is we know our function value is undefined. We know it's undefined. I don't have an actual value. It's just a, the 0 over 0 is called indeterminate form. So that's a hint, something funky is going on. Okay, now let's find the limit as x approaches -3. So we know there's a hole. We know there's a hole for the y when x equals -3. I don't have a y value. But what I want to see now with my step 2 is, am I approaching the same y value from both sides? All right, so the second part is asking, can you predict what the y value would be based on the numbers around where I'm looking, right? So as I'm getting closer to an x value of -3, are my y values approaching the same number, or are they going off into different numbers? All right, so that's our question. So now let's graph this. Let's see. Okay. So I want x squared minus 9 divided by x plus 3. Oh, weird. So it looks like it's a line. We know when x is -3, there's a hole. All right, so I'm looking, let's see, there's 1, 2, -3 right here. So when I go down, there should be a hole right here. But keep in mind, it's literally only at -3. At -3.000000001, it's defined. Right, so the very minuscule parts around it, it's literally only the number -3, not any like -3 point blah blah blah. It's only -3. So the hole is so small you can't see it. We know it's undefined there. We know there's a hole there, but what's it look like the y value is approaching? Let's see. So -1, 2, 3. I go down to this. It looks like it's approaching -6, right? Looks like our limit's -6. So I just traced on my graph to see where it would be. So my limit is -6. So my function's undefined there, but I am approaching the same number. So I'm just gonna draw my graph on here. That should be that. So this is what it looks like. All right, I have a hole. Looks like it's just a line, but x can equal that one number. So secretly, this is the way you deal with it. So if I would rewrite f of x in terms of factors, how do I factor the top, x squared minus 9?
X plus 3, x minus 3.
X plus 3, x minus 3, and the bottom is x plus 3. Oh my gosh. Oh my gosh, what's happening? It cancels. Literally, anytime you have a removable discontinuity, it has the same factor on top and bottom, and when those factors cancel out, that's when you have a removable discontinuity. That was a really weird way of saying it, but when you have a factor on top and bottom that will cancel out, that's when you have a removable discontinuity. Versus, if none of them canceled out and I just had the bottom, then, oh, guess what? I have something left on the bottom of my fraction. It'll just be an infinite discontinuity. But anytime a factor that's on top and bottom will cancel out, you have a removable discontinuity. So what I could literally do is I could rewrite my function as x minus 3, but x cannot equal -3. That's what the graph is showing us. All I have to do is just cut out the one place. That would make me divide by 0, and I'm good. More or less, that's what the graph. So wait, if I would plug in, right, if I would take the limit as x approaches -3 of my new function now that I've canceled my term out, all right, so I just plug this in for x, -3 minus 3 is -6. If you have a removable discontinuity, I'm asking about the x value, where my removable discontinuity is located. After you cancel out the term, You can literally find what the y value would be if it was defined. Okay, so it's getting a little ahead of myself, but I don't know. I think it kind of makes sense showing it to you here. That's not the point. The point of this problem is find the y value. We saw it's undefined. Find the limit. Step 2. We see it's -6. Step 3. Are these the same number? No. Undefined is not the same thing as -6. So we say it's not continuous, and you literally can see it's just removal. All we did is move, just took out one of our y values. Otherwise, it's a nice function. So step 3, is my function value the same as the limit? No. It's not. So this means it is discontinuous. And what type of discontinuity? Removable. Anytime you remove discontinuity, it's almost like you had a regular graph, and as you're going on, you just have a random little hole somewhere. Okay, so our point of discontinuity is occurring at -3, -6, right? That's where it would be occurring. Sorry, I can bring this up a little bit for you to see. Okay, how do we feel about that? Is that okay? We're going to go into more detail later about it. But how do you find continuity test? Find the y value. Find what you think the y value would be based on the limit. And then are they the same thing? Cool. If they're the same thing, it's continuous. If not, it's not continuous. What if, okay, so what if, so I had a removable discontinuity, I have an infinite discontinuity, and then this first example was just continuous. What if I had a function value of 5 and my limit said 4? Is it continuous? No, because my limit is not the same as my function value. That would be a jump discontinuity because it's still, you're defined everywhere. It's just not the same number. That would be the third type. Okay, so now we're talking about end behavior. So the end behavior function describes how a function behaves at either end of the graph. So when we're talking about end behavior, the only parts we care about are literally over here where the arrows are. We don't care about what's happening in between here. Whatever. Who cares? Nobody. Not right now. When we are looking at end behavior, it's when you have a limit approaching infinity or a limit approaching -infinity. So what I mean by that is as x gets smaller and smaller, right? As x approaches -infinity, we're going to the left. What's happening to this y value here for this graph? It's going up, up, up. And when it's going up, going towards positive infinity. Versus this line right here, it's going down to -infinity. If it's going down, like curving down, -infinity. Curving up, positive infinity. If it's like leveling out at a certain number, you would say, oh, it's approaching a certain number. And that would be where you have your horizontal asymptote. But right now, literally, the only answers you can have, 0, because I could have a graph where blah, 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 and then it's approaching 0 like this. Or it could be going like, you see how it's flattening out towards 0? This would be end behavior approaching 0. Versus if I would have a graph that looks like this, blah, blah, blah. Who cares about the stuff in the middle and then goes up this way? I don't know, whatever. Nope, it goes up that way. My two end behaviors, just looking at the ends, toward infinity, up, versus the one in the pink, like as it's going towards infinity, it's leveling off, horizontal towards 0, versus like going up towards positive infinity or down towards -infinity. Yeah? Okay, we're gonna have some practice. So the right end behavior. So as you look at a graph, as you go to the right side, we're saying, okay, limit of my function as x approaches infinity, aka what's happening to y as x just keeps increasing without bounds, as it gets bigger and bigger. So we're not just talking about like, oh, an x value of 5 or 50 or 50 million. We're talking about like infinity. As it goes on and on and on and on, like where's the graph going? Does it just keep increasing, or is it just gonna like go to 0, or is it gonna keep decreasing forever? So for instance, for the example up above, the limit would be going to -infinity because it's just going down and down. So this is the positive direction. Now, if I'm looking at the left end behavior, we're saying what happens to the y values as x decreases without bounds, aka if you go left in the negative direction. And how do you know? Because you're going towards the negative. So when you have -infinity and positive, you don't have to write the plus for the positive. I mean, you can. but you have to say negative infinity if it's supposed to be negative infinity. I don't know. You need to make it clear. You need to make the negative in front of the infinity clear when you're doing your left-hand behavior.
The right side is going towards negative.
Positive. The left side or right side?
The right side, because it's going down.
Oh, the y value is. The y value. But what I'm saying is as x approaches negative infinity. So left-hand behavior as x is going negative. In our example, y is going to positive infinity. Yeah. But I want to do this example. So use a graph each function to describe its end behavior. So I want you guys to have an idea of what it would be. So you see these blue lines, they should have arrows. Just because this is taken off a calculator. This is the way it should look. There should be arrows, all right? So the graph doesn't end at the end of our graph. The lines keep going. Okay, see if you can figure out what the right end behavior would be. All right, so the right end means we're taking the limit of our function as x goes to positive infinity. So meaning as I trace out my graph, what is happening to my y? What number is it approaching? So as x gets bigger and bigger, what is the y approaching? Yes. 0. So we're saying as x gets bigger, so as we go farther right on our graph, we're looking what's happening to y. So remember limits, we're always guessing what the y would be. So our right end behavior, we're guessing what the y would be at the very, very end of our graph. Okay, now let's try the left.
Maybe you don't write what the y would be.
I did, 0. All right, limit of f of x as x goes to negative infinity. Okay, so I'm going further and further left with my x values. What's happening to my y?
0.
It's also going to 0. Notice we didn't talk about anything here in the middle because we are only looking at the end behavior. It's called end behavior because it's not the middle. So as x approaches, we're looking, okay, as I'm changing my x, the limit is asking what is happening to y. So your answer is always going to be describing what's happening to our y values. Okay, take a look at the next example. Okay, keep in mind, we're looking at end behavior. We don't care about what's happening here. The end behavior on the right side versus end behavior on the left side. All right, give it a shot. See if you can get it yourself. When you're done, compare it to the person next to you. Or just turn around. Okay. So, right end behavior, the right end. We say the limit as x approaches what? If we're going to the right, it's approaching in positive infinity. Okay. Of my function. So what this is saying is, look at your x values as you go to the right. What is happening to y? It's getting increasing. Okay, imagine that I could take this graph and zoom out, zoom out, zoom out, zoom out. What's going to keep happening to my graph? It's just going to keep going up. So it's going to be approaching positive infinity. Okay, so I'll make it explicitly clear. But wait, infinity is not a number that we can pin down. Remember how we do square brackets and parentheses? Infinity is always a parentheses because you never can actually point at it on a number line. So when we say a limit of infinity, we also say DNE. Did I already say this to you guys? No, okay. Whenever you have a limit of infinity, you also include DNE. So 2 reasons why. A, you're saying, okay, it's not going to a number, it's just going up and up and up. So saying positive infinity tells me it's going up, up, up. But also this tells me you understand that infinity technically isn't like a number. If I have a number line, then you can be like, it's here. You can't actually locate it because it goes on forever. So technically, the limit doesn't exist because you're not actually approaching a number. You're approaching like lots and lots of numbers, and you're going to keep getting closer and closer and never actually reach it. It's kind of like, I don't know, kind of nerdy, a black hole. You get closer and closer and closer, you're never going to touch it. Yeah.
Well, does it a black hole suck everything in?
Well, this is like relativity. If you're being sucked into a black hole, I'll sit here and I'll watch you forever because like it dilates time and then it like slower and slower. So although I'm gonna watch for my whole life, you'll never reach it. So I'm not talking about from your point of view. I'm talking about from mine. Because you'll go through you'll turn into spaghetti real quick. Okay, I don't know. Maybe that wasn't a good example for this. It doesn't actually approach a single number. So if it's not approaching 5, 10, something you can actually write a number, you say D&E. But if I just wrote D&E, I don't know, okay, so is it a jump? Like what's actually happening in my graph? Oh, okay, so it's going up, but it's technically D&E. Whenever you have a limit that's infinity, you say D&E as well. I did not stress this enough last year. You still have 35 minutes, don't worry. Let's go left hand. Left. What's happening? X approaches negative infinity. What's happening to my function? It's going to negative infinity and you say D&E. So negative infinity says, wait, we are all going one direction. It's not just jumping, but technically going to negative infinity means we don't exist. Okay, so you need both. You need both. Okay, said it 5 times. Need both. All right, and now we're going to use our graphing calculator. Do you guys have it out? Yeah, calculator skills, because if you notice on your practice test, there's a calculator section, and if I let you use a calculator, I'm asking for the zeros, you can sure as heck use the stuff your calculator lets you do. Okay, anyway, use your graphing calculator to graph each function. Identify and describe any points of discontinuity. Describe the end behavior. Locate any zeros. So first step, let's plug in our function. Come on. Okay. Delete this. So I have x to the 3rd power minus x squared minus 4x plus 4. Yay. Look at that. Okay. So, are we surprised that it's continuous? Like, look at it. No, we're not, because it's continuous because it's a, yes, polynomial. What's the domain of a polynomial? All real numbers. Okay, so you literally already have half of this done because you know it. So we're not surprised. This is a polynomial. And we know it's continuous. And that's why the domain is all real numbers. So discontinuity and type, there's none, right? You know the domain is going to be all real numbers. Let me pause here if you have a question, because I might have a little too fast with that one. Okay. So, let me scroll it up. Okay. So, the right end behavior. So, although there's not like technically an arrow right here, you know it's going up, right? You got 2 lobes of the brain. Like you can see it's going up. Wonderful. So, what is that wasn't mean, right? Nah, it's like, okay, that's not an arrow. Like you know it's going up. Right end behavior. As x goes to positive infinity. Okay, ready? So, I'm tracing my x's. As my x goes more right, what's happening to y? Just goes up. So we say infinity D&E. That was a really ugly infinity. Okay. And left hand behavior. What's happening as I go way, way left on my graph? It's going down without bounds. Right? You don't see it's coming back up. Okay, so this is an x to the 3rd function. We're gonna play a game for 2 seconds. Not a game, just making you be extra with me. Okay, ready? What does y equals 0 looks like? Y equals 0, it's a flat line. Come on. Y equals 0. Flat line. Chelsea. Jolie. Eddie. Ready? Just do this. Do this with me. Okay, you're gonna think it's funny, but guess what? When you take calculus next year, you're gonna be like, oh, I know these graphs. Cool, look at you, get an A. All right, y equals 0. Y equals x. It's a line. Do you see me? Look, I have a positive slope. Y equals x. Y equals x squared. Parabola. Y equals x cubed. Okay, this is, look, my fingers are pointing which way my end behavior is. Y equals 0. Oh, literally my end behavior is approaching 0. Y equals x. What's happening as I go to positive infinity? Y goes to positive infinity. What happens if x goes to negative infinity? Goes down. X squared. What's happening to my end behavior? They're both going up. X to the third. One's going down, one's going up. X to the fourth. To fifth. To sixth. To seventh. To eighth. Yeah.
So odd is just.
So they'll face different ways. Even they'll go the same way. What if I had like negative x squared? They both go down. So this is a power rule, and we're going to go on it later. But this is how I know for sure that this doesn't just like go down and then way over here come back up. Right? This is how we know for sure this is the end behavior, because this is an x to the third function. And we know x to the third looks something like this, where it will like come down, up, and then back down. Down, back down. And if you had something squared, you know, okay, it only has one U shape. So we can say with certainty, because we know what a cube function looks like, we know it goes down forever. That's how we know it doesn't like come randomly up again. Nope, bring down, done. And lastly, zeros. So these first 3 questions, I mean, technically, you could have done them in like 10 seconds. How do you actually find the zeros? Okay, so first, how many zeros are there? 3. And you could like say, okay, it looks like -2, 1, and 2, but maybe I'll trick you. Maybe it would be like -1.97. We don't know. I don't know. So, on the calculator portion, if you look on your practice test, you can actually have the calculator find the zeros for you. So I'm going to show you in case you don't know, because I'm not going to tell you this on the test. So you go menu, analyze graph, 0. You go left of your 0, and oh my gosh, look, I found one. Oh, it told me the other one. I found one of them, menu, analyze graph, 0. And you have to go left of your 0, click, scroll to the right, and it will show you it'll show you. And how many zeros do we have to get? 3, because we're crossing the x-axis 3 times. Keep in mind, the word 0, when we're talking about, it means the same thing as solution. The root's the x-intercept. So if you look at your graph and you see how many times it crosses, that's how many zeros you should have. But you also have to be careful because sometimes it may not look like it crosses and it will be very small. Ran into that as well. Okay, so I'm just going to grab this and move it up a little bit. Did you know you can move your text around on your calculator screen? Okay. Making sure. So over here you should write -2, 0, 1, 0, and 2, 0. Notice our zeros, our x-intercepts, have xy coordinates. If I ask for a y-intercept, that also has to have an xy coordinate, because it's a point where 2 lines are crossing. Okay, so I'm going to give you about 30 seconds or so. Try out B, and then we'll go over it together. Try out B yourself. Okay, so discontinuity and type. So we know for sure it's going to have discontinuity because I have an x cubed on the bottom. If you set your bottom equal to 0, wild. Okay, so I know I'm going to have, well, I should probably graph it, infinite discontinuity at x equals 0. Let's see. Actually, you know what? I'm going to do I have a lot of random stuff on my screen, so I'm just going to clear all. So if you need to, you can click menu actions, delete all, and then it would like clear all the zeros and everything you did. So menu actions, delete all. That way I don't have nothing on my screen. Okay, so I want to enter x squared. Oh, I want parentheses around this. That way it's a whole thing on my top. Okay, plus 3x minus 5, all divided by x cubed. Yeah, so there's definitely a discontinuity around x equals 0. Because as you approach from the right side, you see how it goes down. As you approach from the left, it comes up. Wild. So definitely infinite discontinuity, x equals 0. Right in behavior. Okay, so as we go to the right, what's happening to my y? What's y? Is it like going up towards infinity, down towards negative? No, it's shallowing out and it's going towards 0. But as I go to my left, it's also going to 0. And then how many zeros do we have? We see for sure there's one like on the right side of our graph, and it kind of looks like it crosses the x-axis on our left. So just to be clear, I'm going to go menu, analyze graph 0, and I'm going to put it way over here, and I'm going to drag to see, yep, it does cross. All right, that was a tricky one. It looked like there was blue underneath. Sometimes you might have to zoom in. Some of these graphs are not too nice. Menu, analyze graph 0. So here's my second one. There. Pops up both. So I have negative 4.19 comma 0 and 1.19 comma 0. Okay, so we're gonna start 1.4. Really cool. Do we have questions about this? Give you a couple more seconds. Cool. Okay, so extrema and average rates of change. So we're gonna go over this before. We'll cover this before the test, but it won't be. I'm not gonna put this on the test right now. I think overall, yeah, both sections did very well on the quiz. I'd say most people. I mean, I want to say the average was like 90s at least, so it's pretty rad. Yeah, most people either was like, I think everyone got like 85 or above. It's dope. So that's 2 of the 3 sections are on the test. This test last year was one that like brought everyone's grade up, so it should be a good one, as long as you go to the practice test. 1.4, extreme and average rate of change. So, key concept. If we're talking about a function increasing, decreasing, or if it's constant. So I kind of tried to introduce this to you before. You have a question? No? We're good? Okay. So a function is increasing on an interval I if and only if for 2 points in the interval a positive change in x corresponds to a positive change in y in f of x. So now we don't just have to have like a function increasing overall. I could say, oh, between these 2 points I'm increasing, between these 2 points I'm decreasing, between these 2 points I'm constant. So I can break my graph into parts where I can talk about, oh, where it's increasing, where it's decreasing, where it's constant. So this is over an interval only means like, oh, just one section, not the whole graph, just a section of it. So a function is increasing. So when I'm saying on an interval, so on an interval, so I'm well, I mean this right example, the interval is from negative infinity to infinity. Let's see. So we're just going from A to B. And notice my y is getting bigger and bigger as we go bigger in x. So it says f of x is increasing. A function is decreasing on an interval if and only if a positive change in x. So meaning, as you go left to right, We always read the graphs left to right. So as we go left to right here, we see y is going up. As we go left to right here, we see y is going down. That's a decreasing interval. Versus if I'm going left to right between my x's and I'm not changing y, that's a constant. Yeah? Maybe? Yeah, okay. I mean, this is trying not to be tricky. It should be like mostly common sense. And notice you're not being inclusive, technically. So if I'm going between A and B, you're not including A and B because those are your switching points. Those are the points where you're switching. So if I'm talking about, oh, from negative infinity to A, I'm decreasing, A to B, constant, B to infinity, I'm like going down. So you don't include the points where you're switching from one way to another, from increasing to decreasing or anything like that. Okay, make more sense if we do an example. Consider the following graph to determine the intervals in which the function is increasing, decreasing, or constant. Okay, so we want the intervals, meaning the domains. So I want the domain, which is the x values. And I'm going to split my graph up into, let's see. So I'm going to use 3 different colors. Did I mess up? Should I not use this one? So first I'm going to use pink, and I'm going to look for the places where we are increasing. Okay, seems like we're increasing here, and it seems like we're increasing here. Those are like the 2 places we're increasing. So if I want, but where am I stopping? Where do I stop increasing? Like right here at -3, I'm coming to the top of the hill, and then after -3 it starts going down. Versus from 2 to 6, I'm definitely going up. So I'm going from negative infinity to -3. And I'm not including -3 because -3 is where I'm switching from increasing to decreasing. And then I also want the place between 2 and 6. Because that's another place where I'm increasing. As x goes left to right, you see you're going up. Okay, now I want you to find the places where we are decreasing. All right, so we decrease from -3 to 2. And notice at x equals 2, we're switching from decreasing to increasing. And then lastly, we look for where it is constant. All right, so it's pretty flat right here. So it's going to be constant from 6 to infinity. And notice I'm not including 6. Although the function has a y value when x equals 6, when we're talking about the interval where we're increasing, decreasing, we don't include the 2 endpoints. Yes? No, we don't include the endpoints. When we're talking about intervals of increasing, decreasing, we don't include the endpoints. Yeah. Although the function is defined there, so if I was talking about the, like, what is the, you don't include the endpoints of the interval when we're talking about, the function is blank as x increases. The function is constant as x increases from 6 to infinity. We don't include the endpoints. Okay, so to put that in words, the highlighted portion would go in the blank here. The function is blank as x gets bigger, aka as x increases, as we go left to right. How do we feel about this? Yeah. We're gonna have more examples. I think the whole next page is examples. Woo! Which is good. Okay. Use a graph of the function to estimate the interval to the nearest 0.5 unit on which the function is increasing, decreasing, or constant. So here, I'm going to try to color code. Give me 1 second. So increasing, I said, was pink. Decreasing, green. Blue. Okay. So here, 2x cubed. Is this going to be, where is my functions where I'm increasing, where is the functions I'm decreasing, and where do I keep the same? Huh?
Always increasing.
Yeah, trick play. It's always increasing. So it's always going to be increasing. So the slope would become 0 there, but if you're looking like just a little bit left and a little bit right, you're always like checking, you're always getting bigger. Yeah, so you're understanding like the basic, like you see how it like is going to 0, right? How it's like leveling off. Yeah, so that's more of a derivative, that's more of a slope. Here we're always going to be increasing. So negative infinity to infinity. Cool. How about the next one? Increasing from 2 to infinity. Okay. Increasing to infinity, and then we see we're going to be decreasing from negative infinity to 2. And notice that we always go smallest to biggest, left to right. So when I have a negative infinity, even if this was like a negative 2, I'd still write negative infinity on the left because it's the most negative. Okay. Feel okay with this one? Yeah? If so, try out C. Try to do C yourself. Yeah. Hopefully the color coding will help. I'll upload the solutions like this. Do you need more time to write? You good? Do you have questions about C? If not, you can try out D. What was the hardest part of C? What do you think? Just remember not to include the ends of your interval, because if I was talking about the domain, that'd be a little different, because we're specifically saying, you know, where are we increasing, decreasing, constant? Because technically, at the point x equals 3, like it is continuous at this point, right? Because it's defined. But at x equals 3, is this going to be part of the constant interval or the increasing, right? That's why we don't include it, because it technically could be part of like either one. So that's why we just like cut it off. We can't have it be part of more than one interval. Okay, so try Z. let's see, increasing to there, increasing to there. All right. Let's keep going. How many more pages do we have? Like 3? 4? 4? Not bad. Okay, so we discussed things increasing and decreasing. So now we're going to discuss relative and absolute extrema. So a relative max of a function is the greatest value over some interval. It's kind of like we say, oh, the highest peak in LA County is San Gorgonio, right? It's like 12,000 foot in elevation. Whoop-de-doo, right? That's pretty high. That's crazy. But that's not the absolute highest, right? So the absolute max is over the whole domain. So although San Jacinto is 12,000 feet high, if I went over the whole world, what's the actual highest mountain? Mount Everest. Mount Everest, yeah. Kilimanjaro is one of the 7 summits. It is 19,000 feet. It's the highest peak in Africa. But Mount Everest is the highest in the world. But what if we're only looking over a certain interval? So of LA County, San Gorgonio. Of California, Mount Whitney, 14,000 feet. Over North America, let's see, the one in Alaska, Mount McKinley? I think so. It's like 20,000 feet high. That's crazy. If I wanted over the whole domain, over the whole world would be Mount Everest. That would be the absolute max. It's in Nepal. Right? 29,000 feet high. But if I just am talking about over a interval of LA County, of California, between A and B, this is the relative max. Now, if I was sitting in Nepal and I'm like, what's the highest mountain in Nepal? Mount Everest. That would be my relative max. But if I looked over the entire domain, the entire Earth, then I would say, oh, actually, this relative max is my absolute max. Does that make a little more sense, the difference between them? I did not explain this well last year, so I was trying to think about this the way I think about it, because I love climbing mountains. So, relative, you're just looking between an interval. What is the highest? Now, if you screw up on your calculator and you're trying to find max, but secretly you're looking at something that's a min, like if I'm looking for the max, like between these two parts, you see where I am right now? Like between these two parts, it would just be like, oh, well, which one's higher? Oh, this end. But if you want it over the, a certain more different range, it would like look for your highest point, which is here. So notice that the arrows go down forever. So A is a relative. If I was just looking, cross out that one, if I was just looking between these, B would be a relative, but secretly we know B is actually an absolute. It's the highest one of all of the graph. You only can have one absolute. You can have many relative min depending on, where you're looking on your interval. It's kind of like, okay, am I looking in LA County? Am I looking in Nebraska? Am I looking in California? Like, which interval am I looking at? I could have a bunch of different, peaks. But the one big one, that would be your absolute. Similarly, yes? So B technically is a relative max. Well, if we're looking between A and B, let's see. So you only will have one relative max per interval you choose. But if I would have a graph, where'd my pen go? If I had a graph that looks like this. Now, if I choose, so we see this is definitely the absolute of all of it. If I pick my interval from here to here, this is my relative max. If I pick my domain from like here to here, like, oh, okay, I see this is the highest point. So you're only gonna have like one relative that we really are like looking at. Yeah. Okay. What else do I want to say? Okay. So extrema are points in the graph that turn around. So notice we were coming up and then we turned around. We were coming up and then we turned around. So extrema is where you turn around. And notice the rest of the graph goes down. What would have happened if the graph turned around and went up forever? Right, we would have no absolute maximum. We have no absolute maximum because the graph will go on forever. So we wouldn't have an absolute. We would have two relative, but technically. Similarly with the minimum. So notice that like these go up forever. So I won't actually have a max, but I have a minimum. But I have more than one minimum, right? I got this janky W looking character. So f of a is a relative minimum of f. As long as my interval is only like locally around it, that would be my minimum. So it's only a relative, but if it was over the whole domain of my function, then b, where f of b would be the absolute minimum. So it's kind of like if we're looking at, California. Oh, the minimum is, what, the Salton Sea? No, Death Valley. Death Valley is like negative 138 feet in elevation. So that is a local, a relative minimum. But if we're looking over the entire Earth, right, there's these trenches out in the ocean that are like 11,000 foot under water. So that would be the absolute. That is the one place that is the smallest, the lowest for the whole domain, the whole Earth. But you go, I'm like going climbing, I hit all these little relative minimums as I like climb the saddles of these mountains. Okay, I think that was an okay explanation. So let's let's estimate and classify the local and absolute extrema of the graph. So first off, am I going to have an absolute max here? No, because look, my graph is actually going up both directions. There's no absolute max. But I would have one relative max. As long as my interval is like, I don't know, -1 to 1, I could have a relative max. Where is my relative max located? Yeah, 0,3. This is my relative max. Because if I zoomed in just from -1 to 1, right, on that interval, that would be the relative max. That would be great. And what about my min? Do I have an absolute minimum? No, because it only can be one, and they're twinsies. Like, I can't. So I have two relative mins. So at -1, and at 1, -1. Because there's two, there's not one absolute. There only can be one absolute because it has to be king. It only can be one. You can't have two kings. They'll fight until one wins. That's why it's called King of the Hill or whatever. You know that game? Yeah, winner takes all. Like only one can be king, otherwise you have a war. Here, only one can be absolute, otherwise you're done. So there's no absolute max, and there's no absolute min because you only can have one. And when I say relative, I mean local, because I'm only talking about like the small area around it. So that's me and my dialect thing. Okay, so that's pretty rad. We got through a lot today. Cool.